How many?
Is the 1/12 and the 2, is that just because? Or
The 1/12?
the 1/12 and the 1/3? Or the 2/3?
That, with calculus, you can derive those.
Oh, so those,
Yeah, these are, so for a solid sphere rotating through a central axis, that's the moment of inertia.
okay, so those are set formulas?
Yes,
Okay,
they would be on the first page of a test.
alright.
Either in the chapter 8 section or under the formulas too big for the above section. All right, we ready? Ryan's facial expression says yes. We're ready. We were born ready. I have a disk here spinning about its center. The radius of the disk, let's say it's 2 meters. The mass of the disk, put a little subscript D there. This is the radius of the disk. I'm not designed for subtlety. Over here, I have a rod. Let's put it at the length of the rod is 1.5 meters. It is a thin rod. This is a disc. Oh, I never actually put the mass down. Make it 3 kilograms. Thin rod. And let's put the mass of the thin rod to be, what have I not used yet? Let's make it 0.5 kilograms. What I want to know is what is the moment of inertia of this system rotating about that central point? If you need an absolutely stunning visual from it, it's like you've got this kind of setup right here, rotating about the center. Except this would be a disk.
What is the thing that's 2 meters? Oh, radius.
Yeah, right. Radius of the disk. Yep.
This one must be, is there a thick rod?
All right, so yes, there is. The trouble is if I'm spinning this, so I'll take this and I'm spinning it about this axis, that every point at the end is roughly the same distance from the axis. As I get thicker and thicker, so if I get thicker and thicker, then what happens is that these two endpoints are no longer close enough to the same speed.
Okay.
So it becomes a more complicated formula.
We're not worrying about that right now.
No.
Okay.
That is something I would either give to you or I would just subject the 251 students to it. I'd probably give them the formula too. But. Well, moment of inertia is just an infinite sum. Infinite sum of infinitesimally tiny pieces. 15-second aside. We have moment of inertia is equal to the sum I equals 1 to some large number, m sub I r sub I squared. As n goes to infinity, we start dealing with calculus. And so the 15-second aside for those who have had Calc 2. I'm adding an infinite number of infinitesimally small things. So it's the integral of r dm. Oh, sorry, r squared dm. If this means nothing to you, that's okay, it's outside the scope. All right, so moment of inertia is just a sum of a lot of things. So what I can do here is the moment of inertia of this contraption, of this, is the moment of inertia of the disk plus the moment of inertia of the rod. So if I wanted to find my moment of inertia, piece by piece, if I'm rotating about a central axis here, well, human body's not going to be one of them, but I can treat my head as a sphere, neck as a cylinder, torso as a cylinder, arms as cylinders. I can break myself down into various pieces and come up with probably a reasonable estimate for the moment of inertia of a human body rotating about that axis. The disk is spinning about its center of mass, so that's just going to be the moment of inertia of the disk about its center of mass. The rod is not rotating about its center of mass. The rod's out here. So this is going to be the moment of inertia of the rod about its center of mass plus mass of the rod, h squared. Where h is from the center of mass of the rod to here. That is h. Disk rotating around its center is 1/2 mass of disk, radius of disk squared, plus for a rod rotating about its center is 1/12 mass of rod, length of rod squared, plus mass of, I don't know why I put an L there, it should be an R, mass of rod times the distance it traveled that we shifted the axis, which is the radius of the disk plus half the length of the rod.
Is L the weight of the rod plus the radius?
The L is just the length of the rod.
What's the yellow?
The yellow, when you're doing the parallel axis theorem, this h right here is how far you shifted the axis.
Okay,
So we have the formula if it's rotating about its center of mass, and we move the axis to here. So h is that distance,
got it.
which ends up being the radius of the disk plus half the length of the rod.
Okay.
And now it's a plug and chug exercise. Oh, I forgot my square. Now it's a plug and chug exercise. So this becomes 1/2 times mass of disk 3 times 2 squared plus 1/12 times 0.5 times 1.5 squared plus 0.5 times radius of disk, which is 2, plus half the length of the rod, 0.75 squared. Six plus crude estimate, somewhere around 0.9, I think. And plus somewhere around 4, roughly 10.9. Someone is going to tell me an exact number in just a moment. Units. What are the units? And it's not a single word. What did you multiply to get it?
Joule squared? Wait, Joule squared?
Not joule squared. What are the units of mass? Units of the radius. So what would be the units of moment of inertia?
Kilogram meters.
I heard kilogram meters and then it sounded like newtons got thrown into it.
I thought, wasn't Newman's kilograms times meters?
Per second squared.
Second square, I don't know, sometime.
Yep. Don't forget we're squaring the R.
Is Newman's correct though?
No.
Okay.
Let's try that again. Units.
Kilograms. Meters squared.
Yeah, that's it. Kilogram meter squared. If you wanted to throw newtons into it, let's see, that'd be a Newton meter second squared.
Is that what you said we could come up with our own symbol for?
If you want to. I typically don't for this one, but you were welcome to it. So that would be Newton meter second squared. I don't think that's simple, but you be you.
Is that just an approximation, so next to the 0.9 and 4?
Yeah, I was doing that in my head, so.
Oh.
Now notice that the disk is twice the mass of the rod, but the rod contributes more than 50% of the overall moment of inertia. Because that shift adds, it's mr squared. So the distance an object is from the axis of rotation is going to have more impact than the mass. All right, questions to here?
Can you explain the eye of the rod thing? The eye of rod center plus the mass of
All right, so that.
yeah.
All right, I want to find the moment of inertia of the rod. I know what the moment of inertia is about its central axis. I don't have the moment of inertia of a rod rotating about, if that's the rod, so I have it rotating about this point. I don't have it rotating about this point. So I've moved the axis from here parallel to another axis here, which is parallel to the other axis. So two parallel axes, thus the parallel axis theorem. And so I have to take that shift into account. So moment of inertia about the center of mass, the equation we do know, and then taking that shift into account is you tack on the mass of the rod plus how far you shifted the axis. And how far I shifted the axis was, well, I started halfway through the rod, so I shifted to half the rod plus the radius of the disk to get me to the axis of rotation.
Okay. Why does mass come into it, I guess?
Well, we did the derivation
Oh yeah.
on the previous
Yeah.
page.
Yeah.
I mean, the units have to work out also. I mean, this is a mass times a distance squared. That's a mass times a distance squared. This better be a mass times a distance squared. You know what it's time to do? It's time to do some racing. All right. Don't gamble, but place your bets. I don't think we did this last time.
No.
Yes, racing.
Well, we can do it on the floor.
I might have said you racing.
Did I?
Still wonder if I'm ever going to notice something soon enough. I have two objects here. They have roughly the same radius. They do not have the same mass. The ball has a greater mass, as best as I can tell from just holding them. Someone would, Dominic, just confirm, or just tell me which one you think has a greater mass.
The sphere is heavier.
All right, sphere is heavier, but they are roughly the same radius. I'm going to race these down the track, and the question is, which will get to the bottom first? So your options are, and I want you to have an opinion, even if you can't back it up, just go with your gut feeling if you have to. So we have the disc, we have the sphere, tie, and I usually give a fourth choice of neither will make it down to the bottom, they will explode on the way, but we'll just leave that off. Let's just assume for right now they will not explode on the way down. All right, so who says the disc is going to win? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right. Who says the sphere is going to win? Who says tie? There were some people who did not express their opinion. All right, so I got one there. 3, 3, 3. Stone, you want to commit? I'm not going to ask you to justify it. Just pick one or tie.
Wait, how are you pushing it?
I'm just going to put them up here. I'm going to release them at the same time.
The sphere. I don't know.
Wait, that's just my answer.
What do you want? Sphere. Sphere? All right, here we go. The sphere won that one. So let's, I'm going to switch sides just in case there's a forward bias. The sphere won. So congratulations to those three. All right, why?
It's heavy.
The heavier things get the bottom first? Let's test that.
Dude, even I remember that part.
I have two cylinders here. They are made of the same material. This one has greater mass and greater size also. Time to place your bets. Small disc, big disc, tie. Who says the small disc?
Can you, compare the widths?
That's about half the diameter of this. It looks like about half to me.
Oh, I meant like the other way.
Oh.
It's like the same.
This one's thicker. All right, small disc. 1, 2. Was that small disc? Large disc. 1, 2, 3, 4.
I'll go with tie.
And then tie.
Sure.
1, 2, 3. Get the ruler so they start at the same time. And here they go. Darn close to a tie. Let's switch in case there's some forward bias. Pardon?
Looks like the big one's in first.
Did it hit first the first time?
Yeah, looks like it, but it's
Kind
it's
of
so close.
on the
Yeah.
account of it, like, having more reach.
That's fine.
Well, it's the same.
Well, it's
Start.
actually, yeah, it is sticking out just a little bit there. Let's see if I start like,
Then the axis of the.
Yeah.
okay. So congratulations to those three. So Matt, the heavier one did not make it down first.
The shape. The
Okay.
shape of it.
What does shape have to do with it?
They have different equations.
The way it rolls.
This is true.
The way it rolls.
I think the disc has more surface area. Well, like it touches more of the ramp than the sphere does.
Okay, what about these objects have, it looks like about the same width. Same radius. Which one will win? So we have the disc, we have the hoop, and then tie. All right, here we go, disc. 1, 2, 3. The hoop. 1, 2, 3, 4, 5. We have another at the very end. Tie. And then also tie.
And then dish. I'll go with dish.